Hello learners, welcome to this course on Embedded System Design using PIC16F877 microcontroller. In this tutorial, I will be describing about on how to perform a temperature based exhaust fan speed control mechanism. So this application is very simple. We measure the temperature in an environment using LM35 sensor. Based upon this temperature data, we are going to control the speed of a fan. So let us assume the fan is connected to a DC motor. So by varying the pulse width modulated signal to the DC motor, we can alter the speed of the fan. So pulse width modulation is nothing but we will be generating a square wave with different duty cycle. So duty cycle is nothing but T on divided by total time period of the square wave. So how long the on time of a pulse will be there in the total time period of a square wave determines the speed of a DC motor. If my duty cycle is 0%, which means there is no on time at all, in that case the motor will be in off state. If the duty cycle is 100%, which means I have the total period to be an on time, then the DC motor will rotate at maximum speed or rated speed. If I have 50% duty cycle, then I have 50% on time in the total time period of the square wave. Thereby only 50% of the energy is given to the motor. Thereby the motor will rotate at half the speed. Same way I can vary this duty cycle from 0 to 100%. So thereby the speed of the DC motor can be varied. So this is done based upon the temperature value. If the temperature is low, at that time we operate the fan at low speed. When the temperature is high, we operate the fan at high speed. So by measuring the temperature, I can vary the speed of a DC motor. So in order to activate the DC motor, we have to give the necessary voltage for that DC motor to be driven. So that is done using this L293D motor driver. So which is used for providing proper voltage or current to the DC motor. And also it provides an isolation between the microcontroller and the DC motor, thereby the reverse voltage, back EMF will not be entering into the microcontroller. If it enters into the microcontroller, it will damage the microcontroller. So the DC motor is controlled using the 3 pins from the microcontroller, RC0, RC1. So RC0, RC1 control the direction of your DC motor. So 10 will make the motor to rotate in one direction, 01 will make the motor to rotate in opposite direction. RC2 is used as a PWM signal. So here in RC2 pin we will be generating the PWM signal. So thereby the speed of the DC motor will be altered. And we are going to connect a LCD in a 4-bit mode, 16x2 LCD in a 4-bit mode to your microcontroller, where D4, D5, D6, D7 from your microcontroller pins are connected to D4 to D7 of your LCD pins. Same way RD2 is connected to register select pin of LCD, RD3 is connected to enable pin of your LCD. So and the temperature sensor LM35, which has 3 terminals. The pin number 1 is a supply voltage, pin number 2 is a output voltage or current which varies with respect to the measured temperature, and pin number 3 is your ground line. So this LM35 has a linear plus 10 millivolt per degree centigrade scale factor. For every 1 degree Celsius variation, it will produce 10 millivolt as a output variation. So for example, if the room temperature is 30 degrees, the sensor will produce 300 millivolt as an output. If the room temperature is 25 degrees, it will produce a voltage of about 250 millivolts. So it can measure from minus 55 degrees centigrade to 150 degrees centigrade, and it has an accuracy of about 0.5 degree centigrade. And it operates at 4 volt to 30 volt. So this PIC microcontroller, PIC16F877 microcontroller has 8 channels, analog channels AN0 to AN7. So in that we are going to connect LM35 to the AN0 channel, and we have a 10-bit ADC inside your microcontroller. Thereby its resolution If the reference voltage is of about 5 volt, which is nothing but 5000 millivolt, since it is a 10-bit ADC, we have 2 power 10 minus 1. The resolution of the ADC is about 4.88 millivolt. So this is the smallest voltage change which can be represented in a proper binary bit pattern by the ADC of your microcontroller. So if the sensor voltage falls below this 4.88 millivolt, then we need to have an approximation. We will not get an exact binary representation, we will have a little bit of approximated value. For example, let us consider for 20 degree centigrade, the ADC value will be 41. For 50 degree centigrade, the ADC value will be 102. So in order to accommodate this temperature values in a PWM signal, we are going to consider a 10-bit PWM where on time varies between 0 to 1023. 10 bit in the sense 2 power 10. So 2 power 10 is 1024. So 1024 means I am going to have a duty cycle variation from 0 to 1023. So in order to have my ADC value in this range 0 to 1023, I am going to multiply this ADC value by 10. So if I multiply this value ADC value by 10, then I will get 410 and 1020 for this 20 degree to 50 degree centigrade. Then I can give this 410 to 1020 to vary the duty cycle of your square wave generated by the microcontroller. So thereby I get 410 in the sense low speed, 1020 means it is high speed. So thereby a temperature between 20 degree centigrade to 50 degree centigrade can be used for varying the speed of your DC motor. Now let us go and see the circuit part built in a Proteus 8 environment. So here we have a PIC16F877 microcontroller where the oscillator pins, oscillator 1 and oscillator 2 pins are connected to a crystal of 20 megahertz frequency. So this clock frequency will be internally divided by 4 and it will be used for instruction execution. Then the memory clear pin is an active low pin which is connected to a reset circuit here. So by default this pin will be at logic high, thereby the reset operation will not take place. Whenever I close the switch or when I press the switch, the logic low will be going to your memory clear pin, thereby the reset operation will take place. Then we have connected a LM35 temperature sensor to RA0 or AN0 pin. So AN0 pin is an analog 0 channel of your ADC. So by increasing or decreasing this arrow, the temperature of the LM35 can be varied, thereby the output voltage will get changed. Depending upon the output voltage variation, we need to control the speed of a DC motor, and this DC motor is connected with a L293D motor driver. And the supply for the DC motor is given by externally. I am going to give a 12 volt supply plus 12 volt supply, and the motor is driven by two pins RC0 and RC1. So RC0, RC1 will drive your DC motor. The speed of the DC motor will be altered by producing a PWM signal in RC2 pin. So RC2 pin is given to an enable signal, thereby the PWM signal will change the speed of a DC motor here. Then we have a 16x2 LCD which is connected in a 4-bit board, where RD4 to RD7 is connected to D4 to D7 of your LCD, and RD2 is connected to register select pin and RD3 is connected to enable pin. So other power supply lines are connected accordingly. So after building the circuit, we need to create a program to drive the DC motor or exhaust fan based upon the temperature value. So let us go to Proteus environment. So first I configure the LCD to which pins the LCD have been connected. So RS pin of LCD is connected to D2, enable pin of LCD is connected to D3, D4 to D7 of LCD pins are connected to port D4 to D7 of microcontroller. Then I have also declared the corresponding data direction registers, TRIS D2 to TRIS D7. Then I initialize a variable, integer variable, temp value to 0. Then I am going to initialize another variable t equal to 1023. So this is for defining the time period of your PWM signal, total time period of your PWM signal. Then 2 character pointers, then as array to store 5 characters, another variable temp. Then I am going to declare 2 functions. One is software PWM and there is another function for generating the delay. So let us start with the main program. First I declare port A 0th pin to be an input port, because port A 0th pin we are connecting LM35. LM35 is connected to AN0 pin, which is RA0 pin. So this RA0 pin I am setting it to input port, because since we have connected a temperature sensor. So this A is a data direction register. By putting a value 1, the corresponding pin will be configured as input pin. By putting it as 0, the pin will be configured as output pin. Same with TRIS C, we are going to use it for connecting the motors. So we are going to make this port C.F0 pin and port C.F1 pin to be an output pin. Then TRIS D, we are going to connect an LCD. Again, LCD is an output device. So we will be configuring this port D as an output port. Then ADCON1 is set to 0x80 in order to indicate that port A, I am going to use it as an analog port, not as a digital input port. I am going to use it as an analog input port. And the ADC reference voltage is set to 5 volt. Then intcon equal to 0x00 will make the disables to be interrupts to be in disabled state. Then I initialize the LCD, cursor off, clear the LCD. Then I put 2 text temperature based fan control, display it on the LCD. In the first row, first position, I display temperature based, and in the second row, first position, I display fan control. Then in a while loop, I start reading the channel 0 by using this function ADC underscore read of 0. So the temperature will be read and the corresponding hexadecimal value will be loaded onto the temp underscore value. So in order to convert this hexadecimal value into temperature, I multiply it with the resolution of your ADC. So resolution of your ADC is 4.88 millivolt if the reference voltage is 5 volt. So 5 volt divided by 2 power 10 minus 1, which is 1023. So what I do is 5 volt divided by 1023, which is about 4.88 millivolt. So this is the resolution of your ADC. So the temp value multiplied by the resolution will give me the actual temperature. So we already know that our LM35 will give 10 millivolt variation for every degree centigrade. So in order to get a temperature value from the voltage value, I divide the voltage value by 10. So thereby I get the temperature in terms of degree centigrade. Then I convert this temperature in degree centigrade into a string. So integer value is converted into a string and it is displayed in your LCD. We try to display it on the LCD. After displaying it on the LCD, I am going to activate the motor by providing port C.F0 to be 1, port C.F1 to be 0. So the motor will rotate in clockwise and we are going to control the duration of this rotation by generating a software PWM signal. The software PWM signal depends upon the measured temperature value. So this measured temperature value, I am going to multiply it by 10, thereby it becomes in the range of your PWM signal. So this I have said in the earlier slide that for 20 degree I get 410, for 50 degree I get something around 102. So in order to make this 41 to 102 range to 0 to 1023 range, I multiply the temperature value by 10. So thereby it can be used for varying the speed of your DC motor. So when I call this a software PWM, it goes to this function where I set the motor on time, PWM signal on time for a certain time duration. So this time duration duty will depend upon this temp value into 10. Same way off time, which is nothing but total time period minus duty, thereby the on time and off time are generated in a duty cycle. This conference delay duty will provide the delay depending upon your duty value. So if the duty is 100, it will produce 100 microsecond delay. If the duty is 1000, it will produce 1000 microsecond delay. So delay underscore US represents we are going to generate a microsecond delay. So thereby the PWM signal is generated, and this PWM signal will vary the speed of your DC motor. Once the program is done, we can build this program by clicking on this build button. So thereby an hexadecimal code will be generated that you can visualize here. So when I press this in the output file, you can see temp underscore exhaust fan underscore control dot hex file is created. So this hex file I can dump it onto the microcontroller. So we will go to the Proteus environment, right click on the microcontroller, edit properties, select the hexadecimal file, open, set the oscillator frequency to be 20 MHz, press OK. So after dumping the program file onto the program memory of your microcontroller, we need to check whether it is working properly or not. So that is done by using the play button. So when I press that, you can see temperature based fan control. The temperature value is red here. Here you can see LM35 is set with 11 degrees right now, and the temperature value is showing here 11. So and you can see the motor is rotating very slowly. As I start increasing the temperature value, you can see the speed of the motor increases. Right. So 21 degrees, little bit speed is increased. If I increase it further, so up to 50 degrees we can go, because it will come in the range of your PWM signal. So as I start increasing the temperature, the speed of the motor is increasing, or the fan speed is getting increased. You see the speed is increased. So thereby the exhaust to fan speed control can be achieved based upon the temperature data. So in this tutorial I have described about on how to control the speed of a fan based upon the temperature measured in an environment. Thanks for watching. Please subscribe for more technical learning. So you can download the code in this GitHub repository, link given at the bottom. So you can go to this link and you can download the 3 files. One is a C file, hexadecimal file. So C file can be used in your micro C project. You create a micro C project, import that C file and build the code. Thereby you can generate a X file. And I have also included a Proteus 8 project file. So that project file you can build in your system and you can check it accordingly. Thank you.